Bismillahirrahmanirrahim. Good morning, good afternoon, and good evening. Today we are talking about water saturation, and before we go in details, you need to know that there are so many methods for water saturation calculation. We can use Archie Equation, we can use SP log, we can use resistivity logs, and for each and every method there is specific conditions. For example, Archie Equation, which the one we are going to talk about, it's only applicable if the volume of shale is less than 10%. So before deciding which method you are going to use for water saturation calculations, you have to get an idea about what are the restrictions for using any of those methods, and then measure the parameters and then identify the best options. So for example, if you measure the volume of shale or clay volume and you find out that it's more than 10%, so obviously Archie equation is not applicable in that condition, so you have to go for another equation. So there is no tool that can measure water saturation directly. So, there is no tool that can measure hydrocarbon saturation, and that's why we are measuring the water saturation, and then from water saturation we can get an idea about we can estimate the hydrocarbon saturation. And for that, we know, since we are calculating the water saturation, we mainly depends on resistivity values, and those resistivity values are very sensitive to many parameters. They are sensitive to the temperature, they are sensitive to the water salinity. For example, if you can see in this equation that the resistivity of water at room temperature is inversely proportional to the salinity. So if the salinity increase, that means the resistivity will decrease, and the opposite, if the salinity decrease, the resistivity will increase. So this equation, if you know the salinity, you can easily calculate the resistivity at room temperature. Now, how can we change this resistivity from room temperature to the formation temperature? So for that we need to calculate the formation temperature, and this correction is mostly done for most of the porosity, RM, resistivity of mud, resistivity of mud filtrate, and even resistivity of water. And for the calculate or to correct those resistivity values, we need to know the formation depth at which we are measuring this resistivity, the bottom hole temperature, the total depth of the well, and the surface temperature. So, and we apply this simple mathematical equation. We all know this equation, y equal mx plus c. So this is x and this is y. This is the geothermal gradient. The slope of this line is the geothermal gradient, and c, the constant, the part of this interval from the y-axis. So if we have, for example, that our bottom hole temperature is 120 and the total depth is 4,575 meter, and C, which is the surface temperature, is 20. So in order to calculate the geothermal gradient, which is equal the bottom hole temperature minus the surface temperature divided by the total depth, and that gives us 0.022. And going back to that equation and substitute the geothermal gradient, which is m, we know x is the depth, plus c, which is the surface temperature, we can get y, which is the formation temperature. So now we can use this value of formation temperature and substitute it in this equation to get the RW at formation temperature. So this value is RW at room temperature. This is the room temperature value. We already know the room temperature value, plus 6.77 divided by the formation temperature, which we have calculated here, plus 6.77. So it's a very simple, straightforward equations. You firstly calculate the geothermal gradient, which is bottom hole temperature minus surface temperature divided by the total depth. You take the values, substitute it in this value, y equal m, which is the thermal gradient, x is the depth, and c is the surface temperature. There is other methods that can be used to calculate the resistivity to find the temperature at any depth. So for example, in this, using this chart, so we have the bottom hole depth, which is 11,000 feet, and the bottom hole temperature, which is 200° Fahrenheit. So this is our temperature. We go to the x-axis and we look for 200 Fahrenheit, which is this value. Now we have the bottom hole depth is 11,000, which is in the y-axis. This is 5,000, this is 10, so this is 11,000. So the intersection of the two lines is this dot, 200 with 11,000. This is the intersection. We draw a parallel line. So now we need the temperature at 8,000. So we draw a straight line parallel to this line, and until we intersect with the 8,000, which is at this point, and then we can read the temperature, which is slightly, so this is 60, 70, so it's slightly below 170. So as you see here, it's 167 degree Fahrenheit. So both equations, both ways can work. If you get the chart, you can use the chart. If you didn't get the chart, then you can use that simple equation. You calculate the geothermal gradient and then you substitute in the equation. Now if we know the salinity and the temperature, we can find the resistivity of the solution. If we have a solution with a non-salinity and then with a non-temperature, we can find the resistivity of that solution. Simply, in this example, the concentration is 20,000 part per million and the temperature is 75. So we have this is the temperature in Fahrenheit, this is the temperature in degrees Celsius. So this is 75, and those are the concentrations. So we have to look for 20,000, which is this one, this line here. So the intersection of the temperature with the concentration, and then we draw straight line, we can find the resistivity value for this solution, which is 0.3 ohm per meter, ohm meter at 75 degree. Assume that we need to know the resistivity of the same solution at different temperature, because we said that the resistivity is sensitive to the temperature. So the same solution with the same concentration at different temperature will have a different resistivity. So the same solution, if for example you have been asked to calculate the resistivity of the same solution at 150, simply you will just draw a straight line till you intersect with this, with the same line, with the same concentration line, and you just read the resistivity value from here. It's something between 0.1 and 0.2. Let's see another example in which we have the solution resistivity at 75 degree, and we want to find this resistivity of this solution at 200. So the same as I said earlier, you go for the resistivity 0.3, and we have the temperature, which is this one, whenever they are intersecting. So this is the concentration. Now we need to know the solution resistivity at 200. So you just go until you find the 200, and wherever they are intersecting, when the temperature intersect with the concentration, you just read the value is somewhere slightly above 0.1. so it's here 0.115. The thing is, if you use the chart, you might not be as accurate as if you go for the equation. So if you use the chart, the best case scenario that you can get is that something 0.11. But if you go with the mathematical equation, you can find more accurate values. Now let's come to water saturation calculation, and as I said, we will talk about Archie equation. But before just giving you the equation, let us see how Archie find this equation. It's a very simple experiment. It's very simple in the way of understanding, not in the way of implementation. So before that, we have he did the experiment in two stages: before hydrocarbon movement and after hydrocarbon movement, and he simulated the condition in the reservoir before hydrocarbon movement and after hydrocarbon movement. So we have the resistivity of water, in which is the water with the non-resistivity, and we can control the resistivity of this water simply by the salinity. So if we just add salt to reduce the resistivity, and we reduce the salt to increase the resistivity. The original rock resistivity, and in this case we have the value of the resistivity is Rw. We have R0, which is the resistivity of both rock and water. So if we have a rock that is saturated with water, the resistivity value that we get is R0. The third case, which is RT, or the true resistivity, in this case we are dealing with rock, water and hydrocarbon. A rock which is saturated with both water and hydrocarbon. So the resistivity that we are measuring in this case is RT, and this is after hydrocarbon movement, and this one is before hydrocarbon movement. So what Archie have done is he brought a water, he measured the resistivity of water, RW1, and then he put it on a rock sample, and he measured the resistivity, which is in this case R0. So putting in mind that the hydrocarbon saturation is 0, we don't add any hydrocarbon in this case, and the water saturation is 100%. So he saturated this rock with only water, and the porosity is none, it's phi 1, and he measured RW1 and R0, RW1 divided by R0. What he's trying to do is to figure out if there is a relation between RW and R0 or not. He repeat the equation, he cleaned the rock sample, he washed it, and again he changed the resistivity of water simply by changing the salinity, and he measured RW2. It will be different, of course, because we changed the salinity, and he repeated the experiment, and he saturated the rock sample with water, and he measured R0. So he get RW2 and R02. So the values are different from the previous one, and he repeat the equation again, and he get RW3 and R03. What he find that all those the three experiment they are equal to the value as a constant, and this constant he call it F1, and he found out that F1 is equal to A divided by phi to the power m. We will later know what is A and what is m, but for now that's what he found. He found that those values are equal to the division of RW by R0 by R0 is constant value, and this constant is equal to A over porosity to the power n. Now he did the same experiment, but this time he changed the porosity. So he was changing the porosity and changing the water saturation as well. So, and he found out that also the three experiment giving the same constant, and this constant he named it F2, which is different from F1, but it's also equal to A divided by phi 2 to the power m. So the phi is different from the phi in the first experiment. Now let's see what is A and what is M, and he found out that A, what he called it the lithology factor or tortuosity factor, and it's related, it's depend on the lithology in the sense that it's how the fluids are moved through the pore spaces of the specific lithology. So and for that he found out that every lithology have a different tortuosity, different pore spaces and different connection patterns for those pore spaces. So that is A, he called it lithology factor, or in some places you can find it tortuosity factor. M, which is the cementation factor, it's also different from one lithology to another, and it's how those particle or the pore spaces are connected. So this is M, and those value of A and M, they have range depending on the type of the lithology. So A is ranging from 0.6 to 1, and the M is around 2. So you can see that for different lithology we have here for 1.29, 1.082. So in the case if you got a question for calculating the water saturation, but you have not given the values of A or M, so in this case you can just substitute 1 for M for A and 2 for M. Those are the general values. So if you substitute M as 2 and A as 1, in case if you didn't given those values, so that's correct. Now Archie went further, and as we said, he did the experiment in two scenarios: before hydrocarbon movement and after hydrocarbon movement. So after hydrocarbon movement, we said that the resistivity we are measuring is RT, and it's the resistivity of the rock sample which is saturated with both water and hydrocarbon. So in this case the water saturation is less than 1 because we are having hydrocarbon, and the saturation of hydrocarbon is also less is more than 0 because we are adding hydrocarbon. In the previous case it was 0, but now it's more than 0 because we are adding hydrocarbon to this rock, and both water saturation and hydrocarbon saturation is equal to 1. So if we add 90% water, the hydrocarbon will be only 10%. So and so on. Both of them should be 1. So what Archie have done is that he keep on changing the water saturation and measure the total resistivity. How he controlled the water saturation? As we said, simply by keeping both of them equal to 1. For example, in the first time he add 50% water, so that means the water saturation is 50%. In the second experiment, he washed the sample and he inject again both water and hydrocarbon, but this time he injected 70% water, so that means he will inject 30% hydrocarbon, and he measure RT, and so on. He repeat the equation, the experiment with different saturation values, and he measured the RT in each time. So what he found that the water saturation to the power n, and we will see what is n later, is proportional to the resistivity of water by RT. And we can simply remove the proportional sample and add a constant. So that means the water saturation equal to a constant multiplied by RW and divided by RT. To his surprise, he found that this constant is equal to A divided by 5 to the power m, which is similar to F, which we have found in the previous experiment or before hydrocarbon migration. So that means C and F are the same, so he put F in the equation. That makes the equation to be SW to the power n equal A multiplied by RW divided by phi to the power m multiplied by RT. And m is dependent on water saturation, and you call it the saturation exponent. The general value for that is 2, so that's why most of the time you will find that Archie equation is the water saturation equal to equal to the square root of this value. So that's in simplicity, for simplicity. Now let's see an example for that. If you are giving that RW is equal to 0.1 and A equal to 1, M equal to find the water saturation. So this is our equation. RT is 14 and the porosity is 0.5. From where we get this? We get them from the logs. RT is the reading of the deep resistivity in that specific interval, and the porosity, we know that it's equal to neutron porosity plus density porosity divided by 2. Sorry that the scales they are not clear, but those values actually have been measured from the log itself. So now that's make the equation be water saturation to the power 2 equal 1 multiplied by 0.1 divided by 0.15 to the power 2 multiplied by 40, and that will give us the water saturation equals 0.33 multiplied by 100. That's make it 33% water saturation. That's in a very simple way. You just read, you already have A, M and RW. You will get phi from the logs, neutron and density. You got RT from the resistivity, deep resistivity log. Now, as I said earlier, there is always limitation for any technique, and that Archie equation don't put any consideration for clay volume, because as you can see, even in the equation itself, there is nothing related to the clay volume. So this equation is only applicable for clean formation. For example, carbonates. If you are dealing with carbonate, you can use Archie equation. In case of that there is no clay, or the clay volume can maximum reach 10%. If it's more than 10%, so Archie equation is not applicable.